Okay, so let's talk about Beer in terms of Beer's Law and the spectroscopy experiment we just did last week. So let's take a look here. All right, so the learning target, of course, using the spectroscopy to determine the concentration in a mixture of a chemical species. So that was the main target. Next thing we could build a calibration curve using the solutions created by a serial dilution, which you did. You did the 0.4, the 0.2, the 0.1, the 0.05, the serial dilution technique. Use the calibration curve data to calculate the concentration of the unknown. Okay, so let's just start talking about what we're doing here in this lab. Okay, the first thing you did was, in creating calibration curves, perform the serial dilution. Okay, so we have different concentrations. Let's talk about the color of the solution. What was the color of the solution? Blue, right? Okay, and through our serial dilution, we had different shades of the blue. We had darker, and then it got progressively lighter with the less concentrated amounts. Why was it getting lighter? Because there were less of which ion would have been in there making it blue?
Copper.
The copper 2 ion, yes. Okay. And why does the copper 2 ion make it blue? What's going on with the copper? Where does that blue color come from? Why do we see blue? What's going on with the electrons of the copper that are allowing us to see blue?
They're dropping level.
Which specific orbitals are we looking at? The d orbitals, the 3d orbitals, yes, right? That has a lot of wiggle room where the electrons can move around and interact with the water molecules. When the electrons are moving around and jumping around at different energy levels, they're going to be absorbing and releasing energy. And the energy that we see, the blue light, the blue wavelength, okay, is equivalent to how much energy is absorbed. That's going to be what is being released, and that's what we're seeing there, and that's why it has a pretty blue color. Okay, so we set these up so we have the different shades of the blue, so that when we put it in our spectrophotometer, we see the different levels of the absorbance. And the different levels of the absorbance should be giving us our linear relationship. But before we got to our linear relationship, let's talk about setting the appropriate wavelength. Okay, where would we have gotten that from? Well, this should have been in your Prelab, one of these charts in the Prelab. Mainly focusing on this one's out of a 0.1 molar solution, and you pick kind of a middle range concentration, not the high end, because like the 0.4 would have been in the maximum absorbance over here in the 700th. You kind of pick a middle range to get your data point from. And so here we're looking at the best absorbance there was at about 660 was the wavelength to choose, and that's why I had you choose the one closest to 660. Now, I did a kind of experiment with it the night before where I did like a 670, a 680, a 650. I kind of jumped around to see which data was going to give us the best. And it really was the 660 was the best choice in terms of getting the closest for the brass sample. Okay, but you should have looked over here at your graph too, kind of did your estimation here from the line. It should be a little bit over to the right, but it would have been just to the right of the center there, and that's why we would have gone with about 660. Okay, so picking that wavelength in order to choose that. Then we plot our graph, added the best fit line to the equation, okay? And looking at, this is an example of a plotted calibration curve, and you have yours. You need to print it out. You need to use the data in the little box that gives you your equation for the line. But here, down here, it tells us the slope 6.414. Here's the y-intercept, okay? It's a very small number. Now, if it was perfect, there wouldn't be a y-intercept, but it's very small, so we still calculate that in later. And their correlation, 0.9791. We had probably better. Most of us had 0.99 something, 0.998 or something. You guys had really good correlation. with your graphs, okay? And as you can see, like if I was looking at this for sources of error, okay, that, you know, this particular solution, the dot is kind of above the line, this one's below the line, this one's above over here. And maybe, you know, if it's below the normal linear relationship, maybe the absorbance was low, maybe too much water was added and wasn't equal. If it's a little bit above, maybe the not enough water was added, or the equal amounts. So you can think about those along your calibration line as to if your points are a little bit above or below the best fit line, and kind of think about your dilution technique in order to improve it, okay? So that's one thing to pay attention to. All right, so we measured our absorbance of our unknown. We did the brass with the strong acid in the hood. You added 30 milliliters there, brought it to your station, and then diluted it up in your volumetric flask. And our volumetric flasks were 100. Okay. And we got our sample size there. The volume is important. We need to know how much our solution was. Okay, so we diluted it to 100, so we know the volume, because later on we're going to be able to find the molarity. But before we do that, when we're continuing and talking about our brass here, what is brass mainly composed of? Copper and zinc. Okay, so the copper gave us the blue color. What about the zinc? It's colorless, so the zinc shouldn't be affecting any of our data, because the zinc shouldn't be absorbing anything since it doesn't have any color to it. Why does the zinc not have color to it again? Well, it does, it's not a MOM, it is not a multiple oxidation metal, it only goes to +2. And if it's going to +2, that means it's losing its valence electrons, which are in which orbital? The valence electrons are always in which two orbitals? S and P. So it's losing its 2 out of the S. That means the 3D is completely what? Full. So since the 3D is completely full, there isn't wiggle room for the electrons to jump around. So it's not absorbing and releasing energy and showing us a wavelength there. Okay? So that's why it's colorless. Okay, just kind of go back to that atomic level they were talking about that. That's not completely, you know, irrelevant, but it's not totally important for our calculation of our unknown. Just knowing that the zinc wasn't being measured though, and we were focusing on measuring the copper. Okay? So now we're going to use the Beer-Lambert Law equation, and this is how it looks on your formula sheet. So I did it over here looking at it this way. The capital A is for the absorbance. The funny symbol E, that is the molar absorptivity constant. The B is the path length, and the path length is 1 centimeter because that's how wide our cuvettes were. The cuvettes were 1 centimeter width, okay? The concentration is the C here. So this equation's on your formula sheet. You'll be able to use it, and this lab is important. The calibration curve and being able to use Beer's law, that's pretty standard on the AP exam. So I'm going over it extensively, and we will be using this idea again in kinetics. We'll be building another calibration curve. Now the kinetics part will be totally different than what we're doing here, but we will be using this again. And because this is a very important lab, you can completely expect to see a free response on Unit 2 test. Just telling you up front. So make sure that you are taking the time to work out the data and understand the steps here. Now, what happens here is, you know, the absorbance equals the y part of the equation of the line, y equals mx plus b. The EB part, the mole absorptivity and the path length together make up the slope. They make up the m value. The C, the concentration, is your x. Now, we put on the plus b there because, you know, technically if Beer's law, your data was perfect, you wouldn't have a y-intercept, but most of our data wasn't completely perfect, so even I had a little bit of a y-intercept that wasn't right at 0. You still will use that and calculate it in. But this is how you translate it to the equation of the line so that you can figure out the concentration of your unknown using the calibration curve data. Okay? Like I said, I'm posting this on Blackboard so you can go back and refer to it and use it as you're doing your Postlab. Now, looking at an example calculation, what would you do here? In this particular problem, 75 milliliters of a sample of unknown concentration of cobalt-2 chloride is measured to have an absorbance of 0.438. What is the concentration of the cobalt-2 here? And then how many moles is that? How many grams is that? Okay? So refer to the sample calibration curve. So if we're referring to our sample calibration curve, we have its slope. We have the y-intercept, which I rounded to 4 decimal places to keep it in line with the slope there. Then all you have to do is plug it into the equation of the line. Okay, so the absorbance, you know, goes in for the y here. The slope, okay, goes in here. And your y-intercept goes here. And then all you have to do is calculate for x, which is equal to concentration in our Beer's Law example. You know, the Beer's Law equation. So then we know our concentration of our cobalt-2 there. I calculated it's 0.0695. Okay? I went with 3 because this absorbance had 3. Okay? I don't remember if your absorbances had 3 or 4, but you know, you can use it. You can figure out the significant figures from that. Now that I have the concentration, I can figure out the moles, I can figure out the grams. Let me show you how. I know that in my sample that I diluted it to 75 milliliters, right? So I can use the molarity to figure out the moles of the cobalt-2 in there, which you see in the T-chart. Once I figure out the moles of the cobalt-2, I can easily use the molar mass to figure out the grams of the cobalt. Okay? So these are kind of what we're looking for here for the calculations. For your Postlab, that's what I'll be checking. Make sure that your graph is printed out so that I can refer to your data to make sure that you're using your correct slope data. Okay? And if you haven't talked to your group member, make sure they email you, or you can snip it into a Google Doc and share it with everybody so they can print out the graph. That's also a good option, good idea. Other little details to make sure I threw in here. Like I said, pull this up. You can use it to help you write the Postlab. Include the printout of your calibration curve. Write out the data analysis and Postlab questions. Everybody always forgets to write the questions. I don't want people to lose silly points like that. Calculate your percent error for your calibration curve using your correlation value. 1.000 is the accepted value. If you're perfect, you have 0% error. If you're 0.998, you're going to be very small error. Your correlation line's very close. You're also going to calculate the percent error for the percent of the copper in the brass sample. But the Postlab questions kind of direct you through different types of brass samples. I'm having you investigate high brass, low brass, and yellow brass. I want you to look up what their percentages are of the copper to zinc ratio. Okay. Also, researching what kind of things are made out of high brass, what kind of things are made out of low brass and yellow brass. Then you should be able to kind of pinpoint where maybe a brass screw, what type of brass it should be, so that you can calculate your percent error correctly. But most of your data is going to be really close to the accepted value for the correct brass. So that shouldn't be an option. If you're way off, then come talk to me, and I can point you in the right direction if you don't seem to be close to any of the percentages. Okay? But there's a little bit of research in the Postlab, like look those 3 up, decide, you can easily find their percentages of copper to zinc, and then also look up what kind of things are made out of these things. Particularly, our sample came from a brass screw, okay? So you want to be paying attention to that as you're writing it up. Any questions on that? Pretty good? Okay. Once again, the lab's due next week. You want to make sure that everybody's on the same page. And remember, all you're turning in is your data table, your filled-in data table on, okay? I don't need any of the Prelab stuff, like the procedures and materials and Prelab questions anymore. I just need your filled-in data table, your data analysis, your graph, your analysis questions, Postlab, discussion of theory, sources of error, and conclusion. Like those are the sections. And remember, the conclusion rubric, the points are on the rubric now. They're a little bit different than before, so make sure you go back and look at the rubric for the conclusion. You need to state your purpose, whether it was achieved, summarize your results, analyze your results, and then go into the application. And there's lots of applications for spectroscopy, so you shouldn't have any trouble finding and researching those and coming up with, 2 to 3 sentences. Give me an explanation. Don't give me a one-liner, but at least 2